circuit technologies, this program aims to enhance knowledge and foster developments, innovations in semiconductor technologies and their applications. Dr. Abhishek Acharya is the Vice Chancellor of the this field. He obtained his Doctor of Philosophy in Microelectronics and VLSI from IIT Roorkee. Dr. Abhishek Acharya has published over 30 research papers in esteemed national and international journals and conferences, including those indexed by SCI and Scopus. He has six sponsored research projects in his account. His area of interest is modeling of nanoscale transistors, device circuits, interactions. He is the member of various IEEE societies like IEEE Circuits System Society, IEEE Nanotechnologies Council, and IEEE Technical Committee on VLSI. Respected sir, we warmly invite you to share your insights on the topic with us. Thank you.
Right, sir. Sir, I have made you the co-host. You can start the session, sir. Sir, audio is not yet means audible.
So,
Yes, sir. It is audible now, sir.
okay, so now it's perfectly fine from my side.
Yes, sir. Yes, sir. It is visible and audible completely.
Okay, thank you very much. Thank you. So, sorry for this technical glitch. So, I would like to thank Dr. Sarma for inviting me for this session. So, I'll not take much of your time. So, let me directly come to the point of discussion of today's session. So, I'm going to discuss something about beyond CMOS nanoscale devices, its scope and challenge. So, these are the content of my presentation. So I'll start with emerging technologies, then taxonomy for computing, then I'll come to the motivation of today's talk, that is power dissipation, subthreshold slope, and energy efficiency. Then we will discuss about the emerging devices, which are nanosheet FETs, Fox sheet FET, and CFET, and beyond CMOS devices, we have tunnel FET and negative capacitance FETs. At last, I'll discuss something about the emerging memory technologies, which are ferrofet-based non-volatile memories and magnetic tunnel junction-based MRAMs. So I'll discuss everything in brief. So meanwhile, if you have any doubt, you may feel free to you are feel free to ask. So let us start with the emerging technologies. So you can see here that we have some of the trending buzzwords nowadays, which are quantum supremacy, neuromorphic computing, artificial intelligence, and autonomous driving. So you might be aware of the term quantum supremacy, that the calculation or the computation which is done by normal computer in a days or in a months, or in days or months, so that calculation can be observed in the case of ferroelectric materials. So just look at this PV curve, polarization versus voltage curve. We have this hysteresis loop, and whenever the hysteresis loop is there, we can have uh, the options available for memory applications. So look at this case, that memory window here is twice of critical. This EC and TFE. So this is explored in the case of ferroelectric based memory technology. And let me tell you very frankly that in the case of ferrofets, we normally explore the polarization. The polarization I'm sorry, we normally explore the polarization property. All right. So these are some of the the advantages, or I must say, the key features of ferrofet based non-volatile memory. So it has high density as compared to your other SRAM and DRAM technologies. So ferrofet offers a high density. Then we have lower power dissipation as compared to the other technology node. Ferrofets have low power dissipation. Then these are non-destructive readout, which is very important feature, and it's not available in the case of SRAM technology. Then we have good scalability, and the scalability is as good as in the case of SRAM technology. And the one of important aspect of ferrofet based non-volatile memory is that it's faster read and write speed as compared to the volatile memory technology. And at the end, for every memory technology, we have to look at the endurance, and the endurance is also very good in the case of ferrofet, as I told you in the comparison slide also. I'll share those slides with the organizers. So then comes to the next part of the memory, which is spintronics based memory technology. So spintronics is nowadays very promising area. In this case, what happens, we have to use the spin of electron. Otherwise, in most of the conventional CMOS technology, you never look at the spin of the transistor. You just look spin of the electron. You just look at the charge of the electron or the charge of the carrier. So spintronics is considered as one of the most promising future technology in impeding post CMOS era. All right. The second advantage of spintronics is that spin transport. If one has to define spintronics, then spintronics is nothing. It is transport of electrons. It exploits intrinsic spin of electron along with the charge. So just look at this case. I think this animation is not working right now. I'm sorry for that, but you can just log on to this website to find out how this spin of electron takes place. Now I'll discuss very brief about magnetic tunnel junction, because the base of spintronics is magnetic tunnel junction, and this will be used in MRAM. MRAM means magnetic random access memories, and in order to design MRAM, you should have magnetic tunnel junction first. So let us have a look at some brief idea about magnetic tunnel junction. So you see here that we have two kind of layers over there. One is known as pinned layer, and the other one is known as free layer. And insulator will be sandwiched between two kind of layers. So in this case, you just look at these two kind of arrows, that both are in same direction. So it is known as parallel state, and this is known as low resistance state. So the electrons are uh, when electrons are in the same state for both the layers, then it is known as low resistance state. Because in case of resistive RAMs, or in the case of magnetic random access memories, we have to look at the resistances values only. So basically we target the TMR, tunnel magneto resistance over here. Anyway, so this is the parallel state where the low resistance will be offered, and in the other case, you just look at the case when it is, both the arrows are in opposite direction, so it is known as anti-parallel state. So this is known as high resistance state, and with the help of low and high resistance, we normally store zeros and one in the case of MRAMs. So we have two kind of MTGs available with us. One is known as in-plane magnetic tunnel junction, and other one is known as perpendicular magnetic tunnel junction. So most of the time, when it comes to efficiency, perpendicular magnetic tunnel junctions are more preferred choice over in-plane magnetic tunnel junction. So what is the difference between perpendicular and in-plane magnetic tunnel junction? The direction of this spin. All right. So in this case, in both the pinned layer and free layer, the electron will be directed. The spin of electron will be represented by these two arrows. And when these two arrows are in opposite, then it will be considered as anti-parallel state or IE resistance state. And the tunnel magneto resistance is normally defined as the difference between